In this video, we are going to talk about optical activity. In optical activity, we are going to talk about optical isomerism. What is optical isomerism? Optical isomerism is a kind of isomerism in which certain substances change the direction of plane polarized light. So it was first observed and realized in 1811. It was observed that certain substances exist in two forms. One rotates light to the left and the other rotates light to the right. The instance where two substances rotate light in opposite direction is called the enantiomeric forms. So, for example, let's look at enantiomers. Let's assume we have this molecule here, and let's assume that we put a mirror over here. If we put a mirror here, you see that we can draw the same molecule over here, but in this time, this part would come here, CH2, CH3, and this proton will come to this side, and then the CH3 here would be at the side. So it is coming out of the page. So you see that these two molecules are mirror images of each other. However, they are non-superimposable, because if we lift this molecule and we place it directly on this molecule, you see that in this molecule, this CH3 was on the left, but in this place it is on the right, and the CH2 here was on the right, but in this place it is on the left. So if we leave this molecule and place it on this molecule, the various groups are not going to match head on, and for that matter, this molecule and this molecule, they are different, even though they are isomers of the same molecule, and therefore they are called enantiomers. For example, if you take let's assume this is your right hand, and we do a mirror image of your right hand, we are going to get your left hand, and it is going to look like this. So you see that if we take these two and then we superimpose, if we take your right hand and we superimpose it on your left hand, they are not going to match. But your right hand is a mirror image of your left hand. But superimposing the two will not be a match, and therefore molecules that behave in this form are called enantiomers. Now let's take this other molecule. Let's assume we have cyclobutane. So let's assume this is cyclobutane, and then let's draw its mirror image. You see that the mirror image of the cyclobutane is also going to look like this. Let me shade this. So you see that when we take this first molecule of the cyclobutane and we superimpose it on the second molecule, they are going to match, and therefore these two molecules are not enantiomers. It's just the same molecule that has been drawn again. So you see that for these two molecules too, they are also not enantiomers, because if we lift this molecule and we place it on this molecule, you will see that the two molecules will match, and therefore they are not also enantiomers. Now let's come here and draw this ones. So you see that this molecule and this molecule too, they are mirror images of each other. However, if we leave this molecule and then we place it head on with this molecule, they are not going to match, because if we leave this molecule and place it at here is CH3 will be matching OH, and then the protons are in different direction, and this place is OH, and the OH will be matching CH3. So you see that they even though they are mirror images of each other, they are non-superimposable. So these two molecules are enantiomers, and because they are enantiomers, they are going to rotate plane polarized light. What is specific rotation? Specific rotation of a substance is caused by the individual molecules of the substance. So it is when substances rotate plane polarized light. So for example, let's assume that we have a light source over here. So this is our light source with light going in different directions. Then what we will do is that we are going to put a polarizer somewhere here. A polarizer is a device that filters the light so that the light becomes monochromatic. That is, it only rotates in one direction. So you can see that this light source is rotating in this direction. When it passes through the polarizer, the light source will now be rotating or oscillating in one direction. So then what we'll do is that we'll pass it through a tube. We'll pass the light through a tube. If we pass the light through this tube, and the light still comes out in the same direction in which it was oscillating, then we'll see that the compound in this tube is an achiral compound because it couldn't change the direction of the light. However, let's assume that we have another setting in which we use an external source of light. So the external source of light, it oscillates in different direction, and then still we use a polarizer, and then the polarizer would remove all the directions, the light in different directions, so that it begins to oscillate in one direction. Then we'll pass it through the tube that contains the organic compound. So this is the tube. Now, if after the light passes through the organic compound, there is a deflection in the light, so that the light has been deflected from how it was propagating. Let me show the deflection well. So first let me show this deflection well. So you see that first it was in this vertical plane, but now it passed through the tube and then it's been deflected. The tube has a compound in it. So let's say this tube has some organic molecules inside. So in this case, the organic molecule here is an achiral molecule, but the organic molecule here is a chiral molecule. It is chiral because it rotates plane polarized light in different direction, but this one is achiral because it does not rotate plane polarized light. So specific rotation is normally given by the formula. So this is specific rotation. It is given by, and then I'll come back and later explain what these two, the D and the 25, mean. The observed rotation over the concentration of the organic compound times the length of this tube. This is the formula for calculating the specific rotation. Observed angle of rotation. And then the C is the concentration of the solution in grams per milliliter. So C is measured in grams per milliliter. And then the L is the length, the path length of the sample in the tube, and then the path length is measured in decimeters. A 1.00 grams of a compound is dissolved in 20.0 ml ethanol. 5.00 ml of this solution is placed in a 20.0 centimeter polarimeter tube at 25 degrees Celsius. What will be the specific rotation if the observed rotation is minus 1.25 degrees? So from the question, the mass is given as 1.00 grams and it is dissolved in 20 ml ethanol solution. So the volume is 20.0 ml. So we can calculate the concentration. So the concentration equals mass over volume. The concentration is equal to 1 divided by 20.0. So 1 gram divided by 20.0 ml. And this is equal to 0.05 grams per ml. We're also given the observed angle of rotation as minus 1.25 degrees. And then the path length, L, was also given as 20.0 centimeters. But we know that 10 centimeters is equal to 1 decimeter. So 20 centimeters will give us a path length of 2 decimeters. The specific rotation is given as observed angle of rotation divided by the concentration times the path length. So the observed angle of rotation is given as minus 1.25 degrees divided by the concentration, which is 0.05 grams per ml, and then times the path length, 2 decimeters. So the specific rotation is equal to minus 12.5 degrees. A solution is made by dissolving 28.35 grams of pure cane sugar in 100 ml of water. Its optical rotation in a 10 centimeter sample tube is 18.88 degrees counterclockwise. What is the specific rotation of cane sugar? The mass is given as 28.35 grams. And the volume of solution was given as 100 ml. So the volume is 100 ml. And therefore, we can calculate concentration, which is mass over volume. And this is equal to 28.35 grams divided by 100 ml of water. And this is equal to 0.2835 gram per ml. The path length, L, is given as 10 centimeters. So 10 centimeters. And this 10 centimeters is equal to 1 decimeter. And then the observed angle of rotation is given as 18.88 degrees. And therefore, the specific rotation is given as the angle of rotation divided by the concentration times the path length. The observed angle of rotation is 18.88 divided by concentration of 0.2835 gram per ml, then times the path length, 1 decimeters, and this is equal to 66.6 degrees. A solution of a compound 45.00 grams in 250 ml has a measured rotation of minus 25 degrees in 5 decimeter tube. The specific rotation is. So this, you can use this information to calculate the concentration. So concentration equals 45.00 grams in 250 mils, and this is equal to 0.18 gram per mils. And then the angle of rotation, observed angle of rotation, was given as minus 25 degrees. And then the tube, the length of the tube L equals 5 decimeters. So we can calculate the specific rotation, which is given as angle of rotation divided by concentration times the path length. The angle of rotation was minus 25 degrees divided by concentration of 0.18 times a path length of 5. And this is equal to minus 27.8 degrees. We also have another question here. It says that what does the specific rotation of a compound represented as 25D equals plus 9.5 degrees mean? Specific rotation is always measured with reference to temperature and the kind of light that was used in measuring the specific rotation of a molecule is very important. So the 25 represents the temperature. So it means that the specific rotation was measured at 25 degrees Celsius. And the D stands for the sodium lamp. So the sodium lamp was used to measure the specific rotation of this molecule at 25 degrees Celsius. And then the plus 9.5 degrees means that anytime the light is rotated in the clockwise direction, it is a plus. And anytime it is rotated in the counterclockwise direction, it is a minus. So since this is a plus, it means that the light was rotated in a clockwise direction of 9.5 degrees. Let's talk about a racemic mixture. A racemic mixture is a mixture that contains an equal concentration of two optical isomers that rotates plane polarized light in opposite direction. Remember that we said that if you have, for example, two butanol, these two butanol can rotate light in the clockwise direction, and also at the same time it can also rotate light in the counterclockwise direction. So if two butanol rotate light in the clockwise direction, then its enantiomer would also rotate light in the opposite direction, which is the counterclockwise direction. So if we have equal concentration of plus 2 butanol and minus 2 butanol, then we get a racemic mixture, because the mixture contains optically active molecules, but at the end of the day, their specific rotations cancel out. So for example, let's assume that the specific rotation of cholesterol is plus 39.5 degrees, and that is for the plus cholesterol. So we have the plus cholesterol giving us plus 39.5 degrees, and then we have this other isomer, which is a minus cholesterol, which gives us minus 39.5 degrees. If we have equal concentration of these two molecules, then we are going to get a racemic mixture, because the net specific optical rotation is 0. A mixture that contains an excess of one stereoisomer than the other is optically impure. And you can calculate this optically impure is also referred to as enantiomeric excess. So, for example, if the plus is greater than the minus, then that mixture is optically impure. And you can find the enantiomeric excess by using this formula. So, enantiomeric excess is giving us moles of the number of moles of the enantiomer in excess minus the number of moles of the enantiomer of the other enantiomer divided by the total number of moles of both isomers, enantiomers, then times 100%. So this is the formula for calculating the enantiomeric excess. Calculate the percentage enantiomeric excess of a solution that contains 1.5 mole of the plus and 0.5 mole of the minus stereoisomer. So the percentage enantiomeric excess, I'm representing it by EE, is giving us the number of moles of the one in excess, which is 1.5 mole. That one is in excess, minus the number of moles of the other isomer, and that is 0.5 moles, divided by the total number of moles. So 1.5 plus 0.5 equals, so 1.5 plus 0.5, then times 100%. And this is equal to 50%. So it means that the 1.5, the plus isomer is in excess of 50% over the other isomer. And therefore, the optical purity, the enantiomeric excess is also known as optical purity. The optical purity of the solution is 50%. A sample of 2-butanol has an enantiomeric excess of 70% of the minus 2-butanol. What percentage of each stereoisomer is present in the sample? So this sample has an enantiomeric excess of 70% of the minus 2-butanol. So the minus isomer. It means that the excess is 70%, so the other is 30%. So it has So this mixture contains 70% of the minus isomer. It means that the other isomer, which is the plus isomer, and then the minus isomer, they are in an equilibrium of 30%. And this means that, so we will need to divide this 30% into 2. If we divide it into 2, we'll get 15%. It means that the minus 2-butanol is 15%, and it is in equal, so this 2-butanol, let me write it well. So minus 2-butanol, and this is the plus 2-butanol, is also in 15%. So this 15 plus 15% will give 30%. Just that the 2-butanol is in an excess of 70%. So this one is in an excess of 70%, and therefore we need to add 70% to the minus isomer. This then gives us a ratio of 85% of the minus 2-butanol to a ratio of 15% of the plus 2-butanol.